All right, yeah. Thank you very much for the introduction. It's a pleasure to be with you today here and have this opportunity to talk about recent developments in the field of PTA, pulsar timing array searches for gravitational waves, and also the evidence that we now have for the existence of a gravitational wave background at nanohertz frequencies, evidence that has been reported by PTA collaborations around the globe just last year. I will talk about PTA searches for gravitational waves in general to put us all on the same page. I also understand that you already had a similar colloquium on PTAs and gravitational waves earlier this year by Chiara Mingarelli. So the first part of the talk will be a review of some of those things that I guess she certainly also has talked about. And then I will turn to a particular class of interpretations of the signal that we now see in the PTA data. I will look at the cosmological interpretation of the data and think about possibilities to generate gravitational waves in the Big Bang as a possible explanation of the signal that we now have. So this will allow us to probe new physics at the PTA frontier, and in particular with new physics, I mean new particle physics beyond the standard model. But in fact, we can also use PTA observations to probe scenarios of modified gravity. And if there's still some time towards the end, I will also talk a bit about modified gravity. All right, so that's the plan. But to start, let's just put us all on the same page and take a look at gravitational wave physics in general. So I guess all of you, everybody in the audience knows that gravitational waves are ripples in the fabric of space and time, space-time, propagating through space-time at the speed of light and then stretching and squeezing distances on space-time. Gravitational waves were predicted first by Albert Einstein himself in 1916 based on his theory of general relativity. And then pretty much fast forward by exactly 100 years, in 2016, the experimental LIGO-Virgo collaboration announced the first direct detection of a gravitational wave event. So this reached the detectors, LIGO-Hanford, LIGO-Livingston, actually the year earlier on September 14th, 2015. And then in 2017, the Nobel Prize in Physics was awarded for this breakthrough achievement to Rainer Weiss Berry-Barish in Kip Thorne. Now, what's the current status of gravitational wave science, gravitational wave astronomy? Well, on the side of the ground-based gravitational wave laser interferometers, we now routinely observe these compact binary mergers that you can see here in the column on the right-hand side. So these are mergers of either two black holes. This is the most common type of gravitational wave event that we observe, or mergers of two neutron stars, or the mixed combination, a merger of one black hole and one neutron star. You can see an overview of these compact binary mergers, some of them, not all of them, here in this plot on the left-hand side. This is taken from the gravitational wave transient catalog number 3, published by the LIGO-Virgo-Kagra collaboration. And it's already in the name of the catalog. These are transient events of astrophysical origin that stay for a short duration in the frequency band of those gravitational wave interferometers. That frequency band can be referred to as the audio band because the frequencies are around 10 to 1,000 or a couple of thousand hertz. Of course, these are not sound waves. These are gravitational waves, but they are in the same frequency range as sound waves that we can hear with the human ear. All right, but we won't stop here at these frequencies. In fact, just like in the case of the electromagnetic spectrum, there's a whole frequency spectrum of gravitational waves that awaits to be explored. And here's an overview of this gravitational wave frequency spectrum. Frequency is on this axis. And on the right-hand side, we see the audio band, those frequencies around 10, 100, 1,000 hertz, where the terrestrial interferometers operate, and they are sensitive to these compact binary mergers. But now in this talk, I will take you down on the frequency axis by something like 10 orders of magnitude down to the nanohertz frequency range. And this is where PTAs, pulsar timing array observations, operate and search for gravitational waves. And there were kind of big news coming from PTAs last year, because now, since last year, we have evidence for the presence of a gravitational wave background, a GWB, at these very low frequencies. And the emphasis here is on a background, because unlike those transient events that you've seen on the previous slide, the background is something that is constantly reaching us from all directions in the sky, a constant background hum in gravitational waves. And of course, I mean, that evidence is not yet a detection. I will say a bit more about this in a few minutes, but definitely it promises to open a new window onto the gravitational wave universe at these very low frequencies, which are complementary to the frequencies observed by ground-based interferometers. Okay, that's the big picture. Now let's take a look at the results that have been released by PTA collaborations last year. And first of all, we have to review the measurement idea. How can PTAs search and detect gravitational waves? So let's start with the A. With the A in PTA, the array. We have to construct or observe, monitor a network, an array of pulsars in the Milky Way. This is what you can see here in the cartoon on the right-hand side. This is not as large as the entire galaxy. These are pulsars that basically live in our spiral arm of the Milky Way. So these are distances of the order of a few kiloparsec, 1, 2, 3 kiloparsec. All right, and this allows us to construct sort of a virtual gravitational wave detector of galactic dimensions. Each individual pulsar is, I guess, as many or all of you know, is a highly magnetized rotating neutron star. So there's a cartoon, there's this picture here of one individual pulsar on the left-hand side. They are fast-spinning neutron stars, and they also emit electromagnetic radiation. We're particularly interested in the radio emission along the magnetic dipole axis, yeah? So from the magnetic north and south pole. And then typically this magnetic dipole axis is not aligned with the axis of rotation, which turns the pulsar into a cosmic lighthouse. We receive a signal, a pulse, only when this cone of radiation sweeps across our line of sight. Then the pulsar keeps rotating. I can just maybe do it in front of you here on my office chair. We don't see anything. And then after one rotation, the pulsar is back and we receive the next pulse. Yeah, so the pulsar goes blink, 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 blink in the sky. However, it's blinking, it's pulsating much faster than anything I would dare to attempt here on my office chair. And in fact, the pulsars can have stable rotation periods as short as just a few millisecond pulsars. So in fact, for PTA observations, we typically work with millisecond pulsars because they represent the most stable systems. And in a sense, they are ultra precise clocks in the sky. Celestial clocks that give us this highly stable sequence of pulses, blink, 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 that we can use for timing measurements in the Milky Way. So how can we use this now to search for gravitational waves? Let's take a look at the picture on the right-hand side. Again, there even is some kind of illustration of a gravitational wave here. This is this wiggly and stretched coordinate sheet shown in green on the right-hand side. The gravitational wave or gravitational waves coming from the depth of the universe wash through the Milky Way and the spiral arm, our spiral arm of the Milky Way. And then they do what gravitational waves do. They stretch and squeeze the spatial distances. Here in this case, the distances between the pulsars, which are sort of like the freely falling test masses at the ends of our detector arms, the distances between the pulsars and the radio telescopes on Earth. And as these distances get slightly stretched and squeezed, the pulse travel time towards Earth is affected, and the gravitational waves induce tiny distortions in the pulse TOAs, the times of arrival in our radio telescopes. And that's sort of the signature of the gravitational wave background that we search for. Okay, so this is just a cartoon. I've got 2 slides with a few formulas on them so that I can explain what we actually see in the plots later on the vertical axis. So this is again the geometry, and we want to look at the imprint of a gravitational wave onto PTA timing data. Let's just look at one pulsar in the sky, which is located in the direction of some unit vector p. And here we're looking at the simplest possible setup, simplest possible geometry. Let's just consider one monochromatic gravitational wave that moves into the direction of this unit vector omega. And now the gravitational wave stretches and squeezes the distance here, which induces a red or blue shift in this sequence, in this train of pulses coming from the pulsar. And we can calculate that instantaneous redshift from one pulse to the next and to the next and to the next. In particular, for this simple geometry, we find a redshift given like this, which has two factors. The first factor knows about the geometry, so about the direction of the pulsar and the direction of the gravitational wave. And the second term knows about the perturbation of the gravitational background. So Hij are metric tensor perturbations, which encode the information about the gravitational wave. In fact, if you derive this quantity, you have to perform a line integral along the path of the photon. Yes, so basically integrate over the entire geodesic that the photon is, the null geodesic that the photon is following. But then if you perform that integral, you only keep two terms from the boundaries, the integration boundaries of that integral. And one integration boundary gives you the perturbation of the gravitational background at the position of the Earth at the time of observation. This is what we call the Earth term. And the other integration boundary gives you the perturbation of the background at the position of the pulsar at the time of emission. Okay, so that's the instantaneous redshift. However, if you put in the numbers, you will see that this is a tiny, 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 tiny quantity, which we will never be able to measure. The shift from one pulse to the next induced by a gravitational wave. So actually what we have to do is to observe the pulsar, and at the end, all the pulses in the PTA for a very long time, up to years and decades, to see how the effect accumulates, how it builds up and how it integrates up to something that we're sensitive to, that we can measure after 10 or 15 years. So basically we have to wait and see how the gravitational wave, let's say, keeps stretching and keeps stretching and keeps stretching, so that all these tiny redshifts build up to a large timing residual that can stick out of the data and out of the noise in the background. Okay, so then the main PTA observables that we're actually interested in are those integrated timing residuals, where we integrate from the start of the observations up to, well, the entire duration of the observing time, 10, 15 years, for each of the pulsars. All right, so if we do it like this, at that point, we basically just perform some kind of autocorrelation measurement. We've got a time series for each individual pulsar. Still, this is not enough to really dig out a signature of a gravitational wave background, because it could always, I mean, any extra contribution to these timing residuals can always be degenerate with other noise contributions coming from the individual pulsars. So we have to move beyond an autocorrelation measurement and perform a cross-correlation analysis. Yeah, so the hallmark signature, that the fingerprint of the gravitational waves is actually contained in the cross-power spectrum of those timing residuals that I've shown to you on the previous slide. So let's suppose we've got the full PTA, different pulses in the sky, and we can look at the timing residuals for pairs of pulsars, two pulsars, A and B, in the PTA. We cross-correlate those timing residuals, and then we find the following expectation or contribution from a gravitational wave background in the simplest scenario. So if there's really an extra contribution to the timing residuals from a gravitational wave background, and that background is stochastic, Gaussian, isotropic, unpolarized, stationary, and so on, just the vanilla, the simplest case, we find two factors. The first one is a cross-correlation coefficient, which again just knows about the geometry. So this basically follows from the geometric factors or prefactors here on the previous slide. And it turns out it just depends on the angular separation between pulsar A and pulsar B in the sky, the relative angular separation. Doesn't need to know about the absolute position in the sky. If you calculate those cross-correlation coefficients in general relativity for a vanilla type gravitational wave background that I just described, you find this compact closed form analytical formula, which has been worked out by Hellings and Downs in the 80s for the first time. And that's the famous Hellings and Downs curve. I also show it here in the plot on the top of the slide. The red curve is the Hellings and Downs curve as a function of this pulsar angular separation. That's a quadrupole type correlation pattern. So it's positive for close angular separations. It's negative at around 90 degrees, and it turns positive again if the pulsars are back to back in the sky. So that's a quadrupole correlation pattern, which is hard to fake, basically, yeah, almost impossible to fake by any other sources. And so that's really the holy grail of PTA searches for gravitational waves. The second factor here is independent of the pulsars. There's no label A or B. This is a common power spectrum that tells us about the spectral characteristics, the spectral decomposition of the gravitational wave background at different frequencies. In practice, in the analysis with a finite observing time, we've got, actually a Fourier sum here, and then we can quantify the power in the gravitational wave background at different Fourier frequencies. So the power spectrum is related to all the other quantities that you may know that you can use to describe the strength of a gravitational wave background. So here I just tell you how PG is related to the characteristic strain amplitude HC, but you can also express this in terms of SH, the strain power spectrum, or in terms of omega GW, the gravitational wave energy density power spectrum, and so on. So this is just another way to characterize the gravitational wave spectrum. And because we only have access to a narrow frequency range in PTA data, it's actually sufficient to first approximation to just work with a power law ansatz. So that's an ansatz, but we can say within the frequency that we're sensitive to, we just work with two parameters, an amplitude A and a spectral index gamma.
Sorry, Kai, can I ask a quick question?
Yeah, sure.
So it looks from the formula that you're integrating over all f, so this just gives a number, no? So in what sense are you sensitive to this ansatz? If I'm then integrating over all frequencies? And
well, this just tells you that the power spectrum here in this way is independent of time because we work with a stationary gravitational wave background. Still, I mean, here I write down some integral. This is what's valid in the limit of an infinite observing time. In practice, we have a frequency resolution of 1 over t, where t is the total observing time. And then we can actually decompose this here into a Fourier series. It's not an integral, it's a sum. And we can assess how much power is in the gravitational wave background in each individual frequency band. And that basically tells you how strong is the excess timing delay added to everything else on top by gravitational waves on timescales of 16 years or 8 years or 4 years or 2 years and so on and so forth, right?
Yeah, I understand.
So, yeah, I mean, in an ideal case, if you really look at this sort of Fourier decomposition of the gravitational wave background, you could imagine that without any noise and all of that, right, there's sort of sinusoidal contributions from the gravitational wave background at these different Fourier frequencies that we try to reconstruct. Yeah.
Okay, thanks.
All right, great. So this is theory. Now let's turn to data. This is an overview of all the papers from the PTA community that came out in June last year, June 29th. It's been a big effort to coordinate the submission of 18 papers to the archive on the same day. And you see, well, several PTA collaborations were involved. Let's start maybe here in Europe. That's where we've got the European Pulsar Timing Array, EPTA, and they combined the data with the data from India, from the Indian PTA. And that led, for instance, to the first paper here, which is EPTA plus Indian PTA, and they report on evidence for a gravitational wave background. There's a similar paper from NanoGrav, the North American Nanohertz Observatory for Gravitational Waves. As you heard, I'm a member of the NanoGrav collaboration. And for the release of those papers, we mostly actually worked on that paper here. And I will say a bit more about this in the remainder of this presentation, where we searched for signals from new physics in the NanoGrav data. Then there was also, there were papers from Australia, the Parkes PTA, that they used the Parkes Radio Observatory, and also data from China, the Chinese PTA, CPTA, and they also report on evidence for a gravitational wave background. So let's take a look now at the results that were shown in those papers. And we'll just discuss everything that you see on this slide here, step by step. So based on the data, we can try to reconstruct the cross-correlation coefficients. We can try to reconstruct the power spectrum. And then in this power law model, we can also try to reconstruct A and gamma. So let's see how this works. This is the reconstruction of the cross-correlation coefficients, which are supposed to be described by the Hellingston-Downs curve in general relativity. You see the reconstruction from all the different PTAs. These are Bayesian analyses. So what we can actually show here are these blobs. We call them violins. And what such a violin actually is a Bayesian posterior probability density function. So you just have to cut this into half, just slice this in the middle and turn your head by 90 degrees. And then you see the little curve. And that curve is the Bayesian posterior probability density. And we can reconstruct those cross-correlation coefficients here on different nodes along this angular separation axis. In some sense, these plots are mostly for illustration, and they tell you that already by the naked eye, you can see it's consistent with the theoretical expectation, the Hellingston-Downs curve. But you can also perform a frequentist analysis and then do some p-value test. And then you see that the different experiments now really see evidence for the right type, for the expected type of cross-correlation coefficients at the level of 3 or 4 sigma, 3 sigma, 2 sigma, or even up to 4.6 sigma in the CPTA data. What's special about the CPTA data is that they sort of perform a narrowband analysis. So they basically go gravitational wave frequency bin by bin. And there's this one frequency here, 1.5 times some reference frequency, where the significance is 4.6 sigma. But then if they look at the next frequency bin, so 2 times that reference frequency, the significance has gone down to 2.3 sigma already. So this is a different type of analysis. The other PTA collaborations perform a broadband analysis and just take into account information about the gravitational wave background across all the frequencies that they're sensitive to. Okay, so this is the reconstruction of the cross-correlations. Now let's look at the second factor that Daniel was just asking about. Just take a look here. And what we do is we actually multiply by the width of a frequency bin. So if it's not an integral, but a frequency series, for a series, we multiply it by the width of a frequency bin, take the square root, and then that's something that has units of seconds. So this really is an excess timing delay in units of seconds that tells us how much extra delay time the gravitational wave background adds or subtracts to everything else that goes into the times of arrival on different frequency scales. We can again reconstruct this in a Bayesian way. These are these violins here. This is the so-called free spectral reconstruction, where the power spectrum is just allowed to have an arbitrary amplitude at each frequency bin. And we can use this power law ansatz that I was just talking about. The power law ansatz also goes back to the original data and reconstructs the best possible power law fits. And this is what you can see here in terms of those straight lines on log-log axes. So the power law reconstruction is not just a fit through those violins. These are 2 independent reconstructions shown on top of each other. And the fact that they nicely agree tell us that also the analysis is consistent. And now to give you a feel for the numbers, and we also just talked about this a bit, let's take a look here at the first frequency bin in a nanograph. So we can read off a value of around 300 nanoseconds in the first frequency bin, which corresponds to 1/16 years, roughly. So that means that the gravitational wave background adds or subtracts, on average, something like 300 nanoseconds to the pulse times of arrival over periods of 16 years. That's pretty impressive. You can also multiply this by the speed of light. So 300 nanoseconds times the speed of light gives you 100 meters, which means that over times of 16 years, on average, the gravitational wave background stretches and squeezes relative spatial distances by something like plus minus 100 meters, which then causes these excess timing delays that we observe. So that's kind of the size of the signal and the sensitivity that we have. And actually doing these observations for 15, 16 years, or even 25 years in EPTA, we're able to measure these tiny deviations in the times of arrival. Okay, so this is the common power spectrum. And now finally, the power law ansatz, where we have got two parameters, an amplitude A and a spectral index gamma. These are all very similar plots by the different collaborations. If you look carefully, you will see that that's consistent, but it's actually easier if we just put everything on top of each other. So this has been done by the IPTA, the International Pulsar Timing Array collaboration, shortly after the release of the main results. So that paper is from September last year. And they compare the results from the individual regional PTAs. And you see everything is consistent. Yeah, the 1 sigma or 68% posteriors shown on top of each other, they all overlap. And then this is not really a data combination or proper data combination, but what they do is just calculate some naive joint posterior. So in this power law model, A and gamma, just take the product of the individual posteriors and then normalize after taking that product. That gives you a naive joint posterior shown here with the black in terms of the black curves. And again, all of this is consistent. Of course, this is just the first glimpse of such a data combination. At the moment, the proper data combination and then the analysis of that combined data set is ongoing. That's work in progress. And that will lead to the third data release, IPTA DR3.
So in this Venn diagram is showing kind of which pulsars are overlapped,
yes,
the same? Yeah.
Absolutely, yeah. So these are the numbers of pulsars that have gone into those individual PTA data sets here. So this task gives you an idea of how large IPTA DR3, data release 3, is going to be. However, on top of that data, we'll also have data from MERCAT, the MPTA, the MERCAT Pulsar Timing Array in South Africa, and also LOFA in Europe and CHIME in Canada. So it's not only that, but then IPTA DR3 will take the data from all of these collaborations and include something like 120 pulsars, yeah, plus minus, but that's sort of the benchmark or the ballpark that we're aiming for. So it's going to be the biggest and most constraining and most powerful PTA data set ever created. And we can hope to have that data set around 2026, maybe in 2 years from now. That's sort of the current plan. All right, very good. So we talked about theory, we talked about data, we talked about the evidence for a gravitational wave signal that we now have. Note that we have not reached the 5 sigma threshold. This is why I will not really talk about a detection here. What we have at the moment is evidence, compelling evidence, in particular if you take everything together for a gravitational wave background. But of course, we still have to wait until we pass the 5 sigma threshold. But this can, very probably happen with the IPTA DR3 dataset in around 2 years from now. For the rest of the talk, though, I will assume that we are on a good track. And of course, everything is pointing into the right direction. And I will assume that the data and the signal that we now see really is a gravitational wave background. And then we have to ask, if it is a gravitational wave background, where does it come from? And there are 2 options on the table. One is the astrophysical, the other one is the cosmological option. The astrophysical interpretation relies again on black holes. This time it's not stellar mass black holes. This time it's super massive black hole binaries. Here the idea is that we know that basically most of all galaxies in the universe host a supermassive black hole at their center. And we know that galaxies merge. So it's easy to imagine that in the context of galaxy mergers, we form new galaxies that now have 2 supermassive black holes at the center. Those guys, those cosmic monsters, they can find each other and start to form a binary system. And then initially, the evolution of the binary will be driven by the interaction with the environment and dynamical friction. But if that binary should be able to reach a distance of less than a parsec, from that point on, gravitational wave emission will dominate the evolution of the binary. Such a supermassive black hole binary then emits gravitational waves at a characteristic frequency given by its orbital separation. And if this happens across the entire universe, then the superposition of those signals will give us a stochastic gravitational wave background. So that interpretation the SMBHB interpretation definitely is realistic, and I think also preferred by many or most people in the community. It's important to note that at the moment, we have not yet directly seen an SMBHB merger. So a big hope in the community has always been, and it still is, that now we can turn that field into a data-driven field thanks to PTAs, and we can use PTA data to learn more about the evolution and merger history of supermassive black hole binaries. And there are a couple of open questions regarding this interpretation. I will say a bit more about this in a minute, but there has, I think, also been a much more extensive colloquium on this entire interpretation by Chiara Mingarelli earlier this year, roughly half a year ago. So I want to talk now about the second possibility that's also in the title of the talk. That's the cosmological interpretation and the idea that the PTA signal now contains gravitational waves or originates from gravitational waves from the Big Bang, that it is sort of a gravitational wave echo of the Big Bang. Now that idea definitely is much more speculative. The point is that if you just take the standard model of particle physics in the early universe, that will not be enough to give you a gravitational wave background signal that's strong enough so that it would be within the sensitivity reach of current generation PTA observations. So we necessarily must include new particle physics to obtain a strong gravitational wave source in the early universe. At the present stage, this possibility is definitely viable. It's a logical possibility. In fact, we don't know where the signal comes from. It does not have to be of this SMBHB origin. We could even be particularly lucky in the sense that in our frequency band, two backgrounds overlap and just lie on top of each other. That would be kind of a very interesting conspiracy, but it's not excluded, and there could be even two contributions to the signal, astrophysical plus cosmological. In any case, and now in this interpretation, it's possible to, well, think about the dynamics in the early universe and use PTA data to probe cosmology at early times and particle physics at very high energies. And this is what I will say a bit more about now. So let's talk about the possibility to have a gravitational wave echo from the Big Bang. And here's a range of options, the menu of BSM beyond the standard model options to get a strong gravitational wave signal from the very early universe. Option number one is cosmic inflation, the stage of accelerated expansion before radiation domination, before the hot thermal Big Bang. The experts in the audience will know that just standard single field slow roll inflation will not be able to do the job because there are some consistency relations, and that will just give you a red tilted gravitational wave spectrum. So we have to work with non-minimal cosmic inflation scenarios. Axion inflation is one possibility. In any case, in that interpretation, there's a nice complementarity between PTA science and the physics of inflation, which again is related to observations of the cosmic microwave background. The second possibility would be a cosmological phase transition. We require a strong first order phase transition in the vacuum structure of the quantum field theory to trigger the generation of the strong gravitational wave signal. Again, that's something that's not predicted by the standard model of particle physics. The standard model just tells us or predicts two smooth crossovers at the electroweak and at the QCD energy scales. So that doesn't work in terms of gravitational waves. But for instance, if we are able to add some new physics, some BSM ingredient to the QCD sector so that the crossover turns into a strong first order phase transition, automatically we get a gravitational wave signal just at the right frequencies, just in the right frequency ballpark. So that's very intriguing, I think. Such a strong first order phase transition could also take place just in a dark sector involving new degrees of freedom. So this entire idea here has a nice complementarity between the PTA science program and searches for new physics in the QCD sector or in new dark particle physics sectors altogether. All right, the third option are enhanced density perturbations, large overdensities on short distance scales. That's something that's not constrained by CMB observations. And such large overdensities on short distance scales, they can do two things at the same time. They can emit gravitational waves at second order in cosmological perturbation theory, And at the same time, those overdensities can collapse into primordial black holes. It's important to note that these are two things happening simultaneously next to each other. It's not like that the PBHs first form and then emit gravitational waves. Sure, that's something they can do as well. And then there will be another contribution to the gravitational wave spectrum, but that's not what we're talking about here. These are really gravitational waves induced by, in cosmology, we say scalar perturbation. So these are scalar-induced gravitational waves that accompany the production mechanism for the primordial black holes. So here in that idea, in that scenario, there's a nice complementarity between PTA physics and the physics of primordial black holes. And then finally, the fourth option are cosmic defects. These are remnants, leftovers from phase transitions. Again, a phase transition is a transition in the vacuum structure of our quantum field theory. And the remnants, those cosmic defects, are regions in space that preserve the old vacuum structure from before the phase transition. These are regions where the phase transition actually didn't take place. If these defects are one-dimensional, tube-like objects, we call them cosmic strings. If they are two-dimensional sheets, we refer to them as domain walls. And actually, the production of such cosmic defects is a common prediction in many scenarios of grand unification. So again, here there's a nice complementarity between the PTA science program and the physics of grand unified theories. All right, so all of this looks intriguing and interesting, to some extent also pretty exotic. So the question is, does it actually make sense? Should we really care about such exotic sources? Why should I care about these BSM options if there is a reasonable and very well motivated astrophysical interpretation that can actually explain the signal? So do we really believe that PTAs could be seeing a gravitational wave echo from the Big Bang? And just to play devil's advocate here on this slide, let me tell you again about the problems that we have in these different BSM scenarios. So if we think about the inflation scenario, we have to acknowledge that the simplest type of gravitational waves, the vacuum tensor perturbations from single field slow roll inflation, are not enough. There must be an extra source in inflation. For instance, an axion field coupled to gauge fields or something like this. In the case of the phase transition, we have to acknowledge that the standard model is not enough. That just predicts a QCD crossover, a smooth crossover. So again, we have to put in some new ingredients, degrees of freedom, by hand. Also, if you realize such a strong first order phase transition, you have to wonder where the energy released during the phase transition actually goes. And there is the risk, there's a problem that you could create too much dark radiation. So you have to be very careful about bounds on N effective, the effective number of neutrino species. In the case of scalar-induced gravitational waves, well, you need to have those strongly enhanced scalar perturbations in the first place. You can get them from certain types of inflation models. You can work with ultra slow roll inflation, where you put in some extra super flat feature into the inflaton potential. But why should that be there? Why should there be such a feature in the inflaton potential? You could say that that really is signal engineering. Nobody has asked for it, but you just put it by hand to engineer a certain signal that you would like to get out of the entire story. So you maybe have to put in a bit more work to really justify and to find a motivation for why inflation, for instance, should be described in this way. Also, there's a probability that you just produce too many primordial black holes, and there's a high risk of PBH overproduction. And then talking about the cosmic defects, it's also not that easy, because if you just take stable cosmic strings from some grand unified theory, we found in our analysis last year that the gravitational wave spectrum turns out to be too flat. So it's not that easy to fit the data. Also, if you then move on to another class of defects, so-called metastable strings, you can get a steeper slope in the gravitational wave spectrum, and then you can get a nice fit of the data. But for that, there again must be some kind of conspiracy, and those metastable strings must decay just at the right time in the early universe. And you should wonder, why should nature do us this favor and make the metastable strings decay just at the right time, so that now we can explain the signal? So you see, there are a couple of questions and issues. However, of course, I personally believe that there are very good reasons to care about exotic sources. And on this slide, I will just tell you about 3 such reasons. And maybe if you can think about more, we can chat about them. The point is that if you go for the alternative, the astrophysical interpretation in terms of supermassive black hole binaries, you have to acknowledge that the signal is surprisingly loud. It's a very strong signal that nobody had seen coming. You can see this here in the plot on the left-hand side. This is the parameter A in the power law model at the reference frequency of 1/1 year. This is again A, now at a reference frequency of 1/10 years. And those vertical bars correspond to the measured value in the nanograph data. And the green horizontal bars correspond to predictions and expectations from theorists during the last 10, 20 years, or even a bit more, 30 years. And you see that nobody really anticipated, nobody really expected such a strong signal, in particular here at those higher frequencies of 1/1 year. Everybody got it wrong and thought that supermassive black hole binaries would give you a weaker signal. So now we have to think about, if we believe in supermassive black hole binaries as the origin of the signal, can we still explain the data? And we can if we go to unexpected corners of parameter space. So people are now looking into this and realize that you have to, for instance, increase the local density of binary systems by a large factor. So if you just say that there are 10 times as many supermassive black hole binaries in our local universe compared to your earlier expectation, you can crank up the strength of the signal. But then there are maybe conflicts with the observed population abundance of individual supermassive black holes. You also can make the... Yes?
Quick question, Kai. So just looking at these predictions, there's kind of a large spread also in the predictions, but sometimes small error bars. So presumably the error bars are kind of optimistic.
Yes.
But then what actually goes into the spread? Like what's different between different predictions so that they don't agree in detail?
Yeah, that's a very good question. I think, the general context of this discussion is what's known as the final parsec problem. So since a long time, people were actually not even sure whether such binary systems, if they form at the center of a new galaxy, can merge within the age of the universe. We know that at larger separations, if the 2 black holes are further apart than, let's say, a parsec, the evolution is not driven by gravitational waves. The evolution is driven by the interaction with the environment, dynamical friction, and these kind of things. And only then, if you have a chance to harden the binary to make the separation very small, below a parsec of the order of around 1/10 of a parsec, gravitational wave emission takes over and then can lead to the final in spiral and then final merger. And I think for years and decades, people were actually not sure whether binary systems can reach that regime where the evolution is driven by gravitational wave emission. That was called the final parsec problem. And there have been all kinds of proposals. And I think this is what reflects the variety here in these papers. So it's either interactions with stars and gas at the center of the galaxies, then the relevance of 3-body interactions. These are individual stars that go into the binary system. Then there's some kind of slingshot effect, and those stars get shot out again of the binary and extract energy and angular momentum. But then the question is, how many such stars for 3-body interactions are actually available? You have some discussion in phase space of these stars. There's something called a loss cone, where you have to take the stars that can actually go into the system and then extract angular momentum and energy and all of this. So yeah, I think it's the uncertainties related to these effects, interaction with individual stars, with the entire star population and gas at the center of the galaxy, that give you, that are partially responsible for this range of predictions here. Then of course also the number of binary systems, the formation efficiency and all of that. So yeah, it's a very high dimensional problem actually.
Yeah, interesting. Okay, thanks.
Yeah. So I just mentioned a few, but there are really many knobs and handles that you can turn. Another one, for instance, is the delay time. This is the delay between the galaxy merger and the black hole merger. And in the worst case, the galaxies merge, but the black holes never merge. in 13.8 billion years, and then there's no gravitational wave signal. So to really get this high amplitude in the gravitational wave background, you have to have very efficient mergers, which means you have to increase the coupling with the environment. And then you have to ask, okay, is that still physical, and so on. So the conclusion from this is that it's a surprisingly loud signal. Maybe the data is trying to tell us something already at this point. Maybe it's trying to tell us, no, look into some other direction. Maybe it's new physics. Probably not. Let's see. But, and this is what I mean here, ... I think now is a good time to have some hope and to spend some time on these alternative interpretations. The second reason why we should care about exotic sources is that definitely if everything is going to lead to this SMBHP interpretation at one day in the future, we definitely want to maximize our confidence in that interpretation. At the moment, everything is still in flux. There are uncertainties everywhere. And we have to, for instance, improve also the modeling of the noise in our PTA measurements. With better noise modeling and more data, that tension that you can see up here may go away or will go away. So it's very likely to go away. But still, if everything is sort of narrowing in on this astrophysical interpretation, we are still better able to rule out all the alternatives, gravitational waves from the Big Bang. So as long as those options are on the table and there are respectable competitors, we have to make sure that we can kill all these alternatives before we really have maximum confidence in the SMBHP interpretation. And of course, now with this new wealth of PTA data, we can access and constrain new regions of parameter space. So even if the PTA signal is not from the early universe, we can use PTA data and set new bounds, new constraints at the PTA frontier, just constrain those regions of parameter space where inflation or a phase transition or cosmic strings would have given you a signal that would be way too strong, given what we now see in the PTA data. And in this way, you can put new bounds on parameter space, which are complementary to bounds from other frontiers in particle physics, at the energy frontier and intensity frontier. And in this way, even if the PTA signal does not come from the early universe, we can use that data now to identify maybe the most interesting, the most relevant benchmark scenarios for other gravitational wave experiments in the future: LISA, DeSalgo, Cosmic Explorer, Einstein Telescope, and so on and so forth. But of course, at the end of the day, we just don't know at the moment. So this is maybe the hope you can put in this statement here at the very end. At the moment, it definitely is a viable option on the table. And I think it's just the right time now to remain open-minded and agnostic to some extent about the origin of the signal, and then just explore what the implications are if we think about particular scenarios of gravitational waves coming from the early universe. So I think we should care about these exotic sources. And that's what we did. We cared, and we still care about these exotic sources. So we took the Nanograph 15-year data, and we fitted a whole range of BSM scenarios to the data. That's what we did in this paper here, one of the Nanograph papers that came out in last year. It's a bit hard to read, but I mean, these are basically just the scenarios that I talked about already. These are inflationary gravitational waves, scalar-induced gravitational waves from phase transition, and so on and so forth. The blue spectra always correspond to just some BSM source, and the red spectra correspond to this hybrid scenario where two backgrounds overlap on top of each other in the PTA band. So this is a BSM source plus an astrophysical contribution from supermassive black hole binaries. So this is a bigger model where we can just fit all the parameters simultaneously. Now what you can see here is that by construction, those spectra that give you a good fit of the data all look pretty similar. And that has to be like this because it's the same data. So those models now attempt to really reconstruct the same type of signal that we have in the Nanograph 15-year data. So that's not surprising. And what's also interesting now is to do the parameter inference and just ask, if this is the type of spectrum that we need, where do I have to go in the model parameter space for a phase transition, for inflationary gravitational waves, and so on, to get that type of signal? And that's what we did in our analysis here. So beyond each of those spectra, there's a corner plot for the full model parameter space that tells you where in that model you can get such a spectrum. Another observation is that most of these cosmological models are actually well approximated by a running power law. On log axes, a running power law is just a parabola. So you can imagine that if you Taylor expand these spectra in log f up to second order, in most cases, you actually get a pretty good description just in terms of running power law. I will come back to this in 2 minutes or so. Let me also tell you that in our analysis, we performed a comprehensive model comparison. So it's not just parameter inference for individual models, but in this Bayesian framework, we also compare all the models to each other based on the base factor, which is here this ratio of model evidences. In the numerator, we've got the model evidence for either new physics or this hybrid scenario. And in the denominator, it's the evidence for our supermassive black hole boundary standard reference model. And you can see that many of these base factors for gravitational waves from inflation and scale-induced gravitational waves, phase transition, and so on, these base factors are larger than unity, actually of order 10 to 100. Does this mean that we detected new physics? No, of course not. It just tells you that we should take these new physics interpretations seriously. If the base factors all had been 10 to the minus 2, 10 to the minus 3, it would have been clear that we should really not care about exotic sources. The supermassive black hole boundaries give us the best fit. End of the story. But that's not what we observe. We see that those cosmological interpretations are respectable competitors, and they can even give us a better fit in some cases. However, the exact numbers here really depend, are sensitive to all the uncertainties that go into the analysis. So the modeling of the SMBHB signal suffers from many uncertainties. We talked about this a second ago. And of course, the modeling of the BSM sources also involves lots of uncertainties. So my conclusion from this plot is that this is not the end of the story. This is just the beginning. It's a call to action. And for the entire community, basically, we really have to now go ahead and improve the modeling everywhere on the Astro and on the Cosmos side. All right. So how much time do I still have? 5 minutes, right?
Yeah, roughly 5 minutes. Mm-hmm.
Okay, great. Yeah, so I think I still want to mention something in a bit more detail, and then I think I can wrap up and conclude. So first of all, just some brief advertisement, 10 seconds commercial break. If you want to fit your own model to the nanograph data, you can use our tool, PTA Arcade, that performs such Bayesian fits to the nanograph data. All right, and this is also being done by many people now in the community. Actually, what happens at the moment is that people are interested in their own specific scenarios, and they want to know, is my BSM model capable of explaining the PTA signal? So to answer that question, you can perform a Bayesian fit to the data and use PTA Arcade or other tools. There's CAFL. We can talk more about this later if you like. But at present, it's a minority of papers, yeah, something like less than 10% of all analyses.
Kai, there's a there's a question in the room, I think, and please move to the microphone so that we can hear you well.
Yes.
Yes, obviously an interesting topic. Now, when you say inviting people to test out models, obviously that's the data-driven regime that we all want to do. But reading the nanograph paper, it seems that it's a very basic step. Let's say, for example, astrophysical sources, at the end of the day, are discrete sources and not truly isotropic, whereas the cosmological one presumably would be actually much more isotropic intrinsically than the astrophysical ones. So, however, if I say, well, in the nanograph, there are 68 pulsars that go in, so if I calculate the headings and downs, there are 68 squared over 2, there are 2,000 pairs. So that plot is an average of about 2,000 numbers times some frequency bins. But if you look in the papers, it seems that the data, if I just wanted to know those 68 numbers and do the pairwise product myself, that's not available. You can download raw data and spend a couple of years trying to get the produced data. But it seems that the previous step is not, and it says someday it may be made available. Is that something one could try to look at?
Well, I think there were a couple of things here in that question. So definitely, if you want to tell better apart a cosmological and astrophysical signal, then the anisotropies in the gravitational wave background are important. I was planning to mention this in a couple of slides. And well, regarding if you want to do your own analysis, well, I think, I mean, the nanograph 15-year data now is publicly available. I mean, if there's something you still need to perform the analysis, we can maybe talk offline. But then you can just read this into PTA Arcade, and you can specify your model. The model includes the different components, a gravitational wave power spectrum, right? Which is what most people come up with when they think about gravitational waves.
Yes, but there's two different things. In the CMB world, okay, we say you can fit with a power spectrum, which so Planck, you know, they publish power spectra, and you can try to fit to that. And many models, that's all you do. But if you're, since the astrophysical is a non-Gaussian intrinsic signature because it's a bunch of point sources, that requires access to the map level, so not to the correlation, not to the quadratic correlations like headings and downs, but actually to the timing residuals. Now, my understanding from reading the nanograph paper is that the thing that you can download is not the thing that you can do produce that plot, the headings and downs plot form. Maybe it is. If it is, we'd love to.
No. Yes, but at the timing, the timing residuals are available. So that's something you can use, and you can, I think, go back to that step of the analysis. Yeah. Maybe I can provide you with a link later if you like.
Yeah, we'd love to. So your people in this room, half the people in this room are actually working on this problem. Of course, another type of smoking guns. If you ask for smoking guns of astrophysicals, it is first of all non-Gaussian because they're discrete point sources, but also that the pulsar intrinsic term has to correlate because the intrinsic, 68. If you knew the distances to all the pulsars, then you can actually, there is a reason it only goes to a half and not to 1, is because half your noise, half the signal you treat as noise is the intrinsic term. That doesn't have to be that way. So with better distance analyses from scintillation, in principle, one could combine all of that. But again, it requires access to more processed data format than we were able to find. So we'd love to hear more, talk to you more offline of how we could test these.
Okay, very good. Yeah, so this was more like a comment than a question. And I think, I mean, some of the things you were saying are actually on the slides I was still meaning to show. But I think now the time is actually up. Let me maybe try to conclude this one point here, and then I can jump to my conclusions because time is actually up. So I just want to say, yes, Daniel.
But no, you can take a few minutes because we had questions during the talk, and then maybe you can even share your slides if there's something you didn't cover, then I can just...
Yes, sounds good. Okay, great. Yeah, so I just wanted to say that, well, now many people, I mean, you've seen the reactions to the PTA results in the literature, are interested in this question. They have their own scenario of the early universe, inflation or phase transition or cosmic strings, want to know what they can, what that model can explain the nanograph data or the PTA signal in general, can do the full Bayesian analysis based on PTA Arcade or CAFA. What has happened also is that many people just compare their scenarios to a simple power law, this simple power law reference model that I was talking about several times. So again, this is the parameter space in terms of A and gamma for the power law model. And then people just project their predictions for the gravitational wave spectrum onto this two-dimensional parameter space, and then try to infer some information about where and for which model parameters they can get a nice fit of the data. However, in many cases, and we've seen this in the reconstruction of those gravitational wave spectra that I've shown to you, in many cases, the power law spectrum is just a rough approximation of what you actually get in new physics scenarios. Yeah, I was trying to emphasize this here. So in many cases, the cosmological model is actually well approximated by something that looks like a parabola on log axis. This would be a running power law. All right. So what's the conclusion? Maybe you should just not project your new physics model onto the power law parameter space, A and gamma. Maybe you should just perform the Bayesian fit analysis after all, using the tools which are available, PTA Arcade, CAFA, and so on. Or if you want to stay at this level here of the analysis, and maybe even compare different models to each other in some kind of unified common language at the same time, you should work with a more flexible reference model, which would be a running power law model, something that can better approximate the shape of spectra that we see here in these plots. So this is the latest that we've done here, in particular also in my research group in Münster. We now investigated this running power law template model, reference model, in a bit more detail, and just fitted that to the nanograph 15-year data. And then we can reconstruct all these different parabolas, all these different running power law models that give you a consistent fit of the data. And I think it's interesting to compare this to the situation in CMB physics, because also in the case of the CMB, you are interested in reconstructing a power spectrum. In this case, it would be the primordial scalar power spectrum. And you can ask, is there actually evidence for a running in the spectral index of that scalar power spectrum? Well, that's an observable that you can constrain using CMB data. And it turns out that at the moment, the running of NS is tightly constrained. In slow roll inflation, it's suppressed by another power of the slow roll parameters. So I would say that it's okay what people are doing in the field of inflation and CMB physics. And it's okay if you compare your favorite inflation model to just the power law template and calculate AS and NS, and then maybe also R, the tensor to scalar ratio. But as far as the scalar power spectrum is concerned, it's very well approximated just by sort of a pure or constant power law. Now, the situation here in terms of the GWB that we observe in PTA data, the situation is a bit different, because from our analysis, we find that the running of the spectral index is only loosely constrained. So if you call this running of the spectral index, if we call it beta, then that turns out to be of order 1, or the constraints are of order 1, which is the same order of magnitude as the index gamma itself. So we would argue that if you want to stay at this level of the analysis and basically put everything into one, map everything onto one sort of master reference model, it would be better to take your favorite GWB model and map it onto the running power law template. Now you can do it thanks to the paper that we just had in August. So we reconstruct the parameters of this power law model, the running power law model. It's A and gamma again, but now there's beta, which is the running of the spectral index. And in fact, if you want to map your new physics scenario onto such a template, a reference model, you should not map it onto this parameter space, A versus gamma, but you should map it onto this corner plot, and maybe in particular onto this panel, A versus gamma, and then work with the posteriors that you see here in this plot to get some idea of how well your model can actually fit the data. Okay, so this was just a last comment, and I think, yes, now my time is really up. There's, well, one brief comment I wanted to make is that PTA physics can not only take us back to the early universe and tell us something about gravitational waves from the Big Bang. This was the main theme of this talk. It's also sensitive to new physics on other length scales, for instance, dark matter in the Milky Way, or supermassive black hole binaries embedded in embedded in dense dark matter environments. And it's also sensitive to modified gravity. So this is maybe just a teaser or an announcement. You can take a look at the slides later. So there can be new physics effects on all of these length scales, not only just in the early universe. So there were 3 slides I was meaning to show. You can take a look later. And now, as far as the outlook is concerned, we already just talked about it. We cannot just stick to spectral information. Just a spectral reconstruction of the signal will not be enough, because we only have access to a narrow frequency band. Many of those signals that we talked about look very similar, and just by getting a very precise reconstruction of the spectrum, it will be very hard to pin down the origin of the signal. So it will be important to look at complementary observables. Number 1, the first complementary observable would be anisotropies, because in the case of the astrophysical interpretation, supermassive black hole binaries, we have a discrete source population. It's not like some continuous source in the sky, which means that we expect a much higher level of anisotropies. At the moment, we have not yet seen any such anisotropies. So you can imagine, or you can ask yourself, if there should be no detection of anisotropies with future data sets, and the signal should remain smooth, with more and more data across the sky, what does it mean? At some point, this would be a hint of a primordial origin, just a smooth gravitational wave background from the early universe. And then the second complementary observable, we also already had a comment on this, are continuous waves from individual nearby supermassive black hole binary systems. At the moment, we have not seen any such continuous wave signal, just some interesting hints, but at the moment, we just put upper limits on the gravitational wave amplitude in the sky. Of course, if an individual binary should be detected in the future, there would be very strong circumstantial evidence for the astrophysical interpretation of the signal. So this brings me to my summary. I talked about the evidence for the gravitational wave background that we now see in PTAs. There are two options on the table for where the signal could come from. The astrophysical interpretation involves supermassive black hole binaries. There can be new physics effects here. So the green boxes refer to new physics. The supermassive black hole binaries could be embedded in a high dark matter density environment. There are many cosmological interpretations, namely cosmic inflation, a phase transition, scalar perturbations, cosmic defects. On top, there are signatures of new physics not related to stochastic gravitational waves. There can be extra timing delays coming from new physics in the Milky Way. I didn't really talk about it. Ultralight dark matter or dark matter substructures. Modified gravity can affect everything in PTA observations. And if the astrophysical interpretation should be the correct one, we hope to see anisotropies in the GWB soon at some point in the future. And we also hope to see a continuous wave signal from an individual binary at some point in the future. So that's the situation. And the prospect is that the combined information on the spectrum, the anisotropies, and the continuous waves, plus maybe searches for gravitational waves at other frequencies and also observations of the CMB, the combination of that information will allow us to pin down the origin of the PTA signal. So this is not the end, this is just the beginning. And I would say there's a bright future for gravitational wave science with PTAs. The current status is that we now see a common spectrum process. There's 3 to 4 or maybe even 4.6 sigma evidence for the right type of cross correlations, Hellings and Downs. The next step will be to confirm this at the level of 5 sigma. We'll keep measuring the spectral shape, but we also want to search for anisotropies across the sky, continuous wave signals. And the promise is that this entire field, this entire program will lead to deep insights into galaxy and black hole evolution and or, fingers crossed, new physics. So stay tuned and thanks a lot for your attention.
Thank you very much. Thanks for the really nice and clear talk. We're a little bit over, but I think if you still have time, maybe we can take a few questions.
Of course, I can still stick around for a bit.
Okay.
I may question again on the astrophysical side, since Daniel did ask why these things are all over the map. So obviously, it is certainly possible, as we heard from Kai, that there is negligible gravitational wave background from the known supermassive black hole binary, simply because there's a final parsec problem. They may, if whatever you think solves the final parsec problem is some viscous effects, makes them merge all the way without any emission of gravitational waves, and it could be arbitrarily small. However, in the other direction, there's an upper bound, which is that we kind of know omega of black hole. Well, people think they know omega in black holes nearby, which is quite small, 10 to minus 10 or something like that. It's a fairly small amount of matter is in supermassive black holes. And then you say, okay, so then omega gravitational waves is some fraction of that actually is straightforward, quite precisely computed by merger templates. And that's again a small number. And then if you convert this, so at least the talk I heard by Gabriela Sato-Polito, she claims that even if your conversion efficiencies were perfect, and every single black hole you see was a merger of exactly 2 equal mass black holes, the best you could ever do at 0 redshift, okay? In the very best of best scenarios, it is still difficult to achieve the current signal level. So in that interpretation, in her statement was much stronger than what Kai said, right? So she says that it's unlikely to be astrophysical sources. So I just want to, I think that's what you were trying to say.
Yeah, thank you very much for this comment. I mean, I know that paper very well. That's with Matthias Zaldariaga. They have 2 papers now on this, and maybe you've seen this on the archive. The first paper had the catchy title, "Where are nanographs black holes?" And there I think they just did a comparison to the power law model, and now then there was a second paper earlier this year where they actually look at the violence that I showed to you. And everything you're saying is fully correct. It's funny because I'm just coming back from a workshop in Italy where Matthias Zaldriaga was talking about those papers and explaining everything in detail that you just said. Yes, so if you take the data at face value and you say, okay, let's see, those measurements, this amplitude and this spectral index, that's what's in this data, and that's what we should trust. There definitely is a problem. But Matthias Zaldriaga, the co-author on this paper, said that in no way ever would he now jump to the conclusion that it must be new physics from the Big Bang. He says that, I mean, just ask him, he will tell you. He said he's old, he's conservative. For him, it's enough if the order of magnitude is the same, and then there is an astrophysical interpretation. It's off by a factor of 5 or 6 or something like this. At the very beginning, when we first see the signal for the very first time, this is absolutely good enough. And now for 10 or 20 years more, people will have to work on it and see how everything moves in this parameter space and eventually just meets in the middle. So it's true that if you take this data at face value, then even under the most conservative assumptions, the upper limit on the strength of the gravitational wave background from supermassive black hole binaries will not be able to reach up here, and that you can't just do it. That's the point. However, I think what's very important is that maybe we should not take the data at face value. And this is what I'm saying here. Tension may go away with better noise modeling and more data. We're just kind of in a gray zone at this point. The strength of the signal basically is as large, as strong as the strength of all the different noise contributions. It's not like a very high SNR measurement where the signal is much, much stronger than the background. So at this point, it's really difficult and to tell apart what is signal, what is noise. It can easily be that we misattribute contributions to the noise, that we misattribute this to the signal, or vice versa. For instance, all the different PTA collaborations, they use different noise models for the pulsars. We include white noise, we include pulsar intrinsic red noise. In nanograph, it's pretty simple. It's a phenomenological power law description for the red noise. PPTA, for instance, the Australians have more sophisticated noise models. And this is also part of the reason why in PPTA, with those, let's say, more sophisticated or better noise models, the significance also is just 2 sigma and not 3 to 4 sigma. So I think that what's very likely to happen is that everything is still going to move. The modeling of the supermassive black hole binaries, of course, also the modeling of new physics sources, but also the noise modeling. So maybe I can just show this plot here. This is, again, the parameter space of the power law model. Green is the nanograph 15-year data, just taken at face value. The blue contours are the simplest type of SMBHB evolution model that you can think of. This is just circular orbits and purely gravitational wave-driven orbital evolution. They don't really match. I mean, there's a tension here at the level of 2 sigma. At face value, the signal is too strong and the spectral index is too low. But I think, I mean, maybe it's not even my opinion, but I think what many people in the community think is that the green ellipses here will still definitely move a bit to the right, and they will definitely also still move a bit down if we're able to improve the modeling of the noise, the pulsar intrinsic red noise, which definitely can still be modeled in better ways than what's being done in the data analysis right now.
Okay. Yeah, maybe so far there were only questions from me and Whaley. So other questions from anybody else?
But of course, I mean, I know those papers by Matthias Zaldriaga and company. I mean, we have to be very careful here in this business. And I mean, of course, if we can show it's new physics in the early universe, this would be a major breakthrough. But I think those papers that they've written, they contribute to this statement here. So probably not, but ... Yeah, so for me, there's a bit of hope that there could be a cosmological contribution to the signal.
Yes, yes.
On cosmological, you had this comment somewhere opaque hidden in a third bullet that for the scalar conversion, or if you just have the scalar power, that makes both gravitational waves and primordial black holes, that you might overproduce PBH overproduction. There we go. So that I think is only the case if you use Daniel's formula that he calculated a decade ago or more. I think in our more recent hydro simulations with Neo-Turok, we think that the shock waves actually dominate the gravitational wave production, meaning for a given PTA amplitude, there are orders of magnitude fewer PBHs. So that actually, I think, is numerically no longer a problem.
It's true. Yes, I think, I mean, my understanding, maybe you know more about this, but my understanding is that I think this entire calculation of the PBH abundance still suffers from very big uncertainties. There are different formalisms that you can apply, press-Schechter, peak theory. You have to know what is the critical threshold for PBH production, what's the right window function, and all of this. And then, I mean, I've never really worked on this, but I mean, when I talk to people who do those calculations, they tell me, I mean, you see the plots and you take some parameter in the scalar power spectrum, and then the amplitude, for instance, and you vary this by a tiny bit. You vary the amplitude by 10%, and then the final PBH abundance changes by 10 orders of magnitude. And I think what people say is that at this point, we really just don't have the final confidence in those calculations yet. We can't really be certain about those values up to,
I would have the opposite, that because, you know, omega PBH is at most 10 to minus 10 at the time if you produce them in the radiation era, then if it's Gaussian, then you know that these are 5 sigma events. They're very, very rare. So I would have said, I mean, it's true that if you change the amplitude at 5 sigmas by a little bit, that's a huge change in black holes, but that's irrelevant because you're going to normalize that omega black hole is no bigger than omega cold dark matter, no bigger than 0.27. So that's a number that's observed, that goes in. Okay, then that doesn't matter anymore. You don't need to know that. And whether it's 10 sigmas or 11 sigmas really doesn't matter on this, because that's only a 10% correction. You're completely dominated by measurement errors. So I actually feel that obviously it may not be Gaussian. If it's non-Gaussian, then you can actually be off by arbitrary orders of magnitude. But in the Gaussian perturbation limit, it seems, it looks to me fairly robust.
I mean, the point is that, I mean, already when you convert from curvature perturbation to density contrast, you pick up non-Gaussianities, right? And then people also look at non-Gaussianities in the primordial curvature power spectrum. I mean, that's something that has been discussed now after those PTA results. For instance, if you include negative non-Gaussianities, then it's actually easier to fit the signal and avoid PBH overproduction.
Actually, well, maybe I can. Sorry, Willy, one second. Can I maybe suggest we kind of close officially the seminar? I also stop the recording, and then maybe we can keep chatting. Of course, I can keep the Zoom open. Okay, let's thank Kai again for the really nice talk, and